So today we're going to start a topic called systems of equations. This relates a lot to what we were doing with functions and graphing in the coordinate plane, although you're going to see that most of the work we do this week is algebra and solving equations, not really too much graphing. But a good place to start here is, let's talk about the goal for today. The goal is to solve a system of equations using the substitution method. So there are several methods for how to solve a system of equations, and just depending upon the problem, you're going to have to use your judgment to determine which is the best method to use. But for today, we're just going to focus on this one. But before we get into a system of equations and start doing all the work of solving it, it's important that we know what a system of equations is. So let's answer this question first. It says, what is a system of equations and what does it mean to solve one? Good. This is a good place to start. Okay, so here we go. Here's a graph, and I have two equations graphed on it, and I've color-coded it. So there's two equations, two functions here. They're both in slope-intercept form, and they're both graphed. This one here is a y-intercept of -2, slope of 1/3. This red one has a y-intercept of +1, slope of -2/3. Now, this is a system of equations, and it's really simply defined. A system of equations is just any graph that contains more than one equation on it. So it's just not a single line graphed in the coordinate plane, rather it's several. So in most cases, we're going to find the solution to just two equations, although for sake of argument, we could find a solution to 3, 4, 5, or any number of equations. And what we mean by solving it is actually a really simple idea. We just mean where these two lines intersect. That is what it means to solve a system of equations. What point do they share? I know that there are infinite points along this red line, and that any of those x and y pairs, all of those ordered pairs along this line, will make this equation true. I also know that there are infinite ordered pairs along the blue line, and that all of those ordered pairs x and y will make this statement true. But what we're doing when we solve a system of equations is we're looking for just that one ordered pair. There's only one. That one magic ordered pair right here that will make not just one equation true, but both of them. Now in this one, it's really easy to tell what that is. It's just 3, -1 because it's graphed for you. Now I won't do the work of this. I'm just going to let you take my word for it. But if I were to plug in a 3 for x and a -1 for y, both of these equations would balance out. This is a solution to both. So that's what we mean by finding a system, solving a system of equations. Thing is, most of the time, we're not going to have graphing available to us. In fact, we're going to jump right into one like this. And this is a system of equations. You can see we have no coordinate plane to work with. Not only that, but the equations aren't in slope-intercept form. Here's the thing. It doesn't matter. We don't need it. And we're going to learn several methods this week for how to solve them. Now, the first one is called the substitution method. You're going to see why it's called that in just a second. And I'm going to start with this first equation here. This one you can see is simpler than this one. This one's a little bit more complicated. And no, you don't have to get it in slope-intercept form or anything that we've done in the past. What I'm going to do is I'm going to take this equation here and I'm going to solve it for y. All right, and I'm just going to do that by rewriting it as y equals 15 minus x. And I'll let you sort of look at that. Do you see what I did there? All I did was subtract x from both sides. And I don't need to write it in any special way. All I'm doing is getting this variable by itself. And I see that that's really easy to do. So I just got y by itself and moved the x over, 15 minus x. Now, look at what I've done here. I have now defined the variable y as this expression. So what I'm going to do now is I'm going to look in the second equation for y. Where's the y here? Well, it's right here. And instead of writing y, I am now going to substitute, hence the word substitution. I'm going to substitute this entire expression because watch what happens when I do that. Now we have 4x plus 3 times 15 minus x equals 38. Now we have a linear equation with just one variable in it, and now we can solve this. So when I do that, well, we're going to distribute the 3, right? So we're going to get 4x plus 45 minus 3x equals 38. Okay, now we keep solving. So I combine my like terms. I have a 4x and a 3 and a -3x. That's just going to give me x plus 45, is equal to 38. And then finally, we subtract 45 from both sides, and we just get x equals negative 7. Okay, so now we've found the x-coordinate. So by substituting this expression for y in this equation, I got rid of the y's, and now I solved for x. Most of the hard work is done at this point. So x is equal to negative 7. That's half the answer. Now we just have to find out what y is. And you can do that by plugging this x value into either equation. I recommend the first one because it's a bit simpler, right? So if x is negative 7, well, negative 7 plus y equals 15. And then I'm just going to add 7 to both sides. So I get y equals positive 22, just adding 7 to both sides. So our answer is the solution to this system of equations is negative 7 and 22. Now let's just look at one more example here. And I'm going to show you a slightly different way of solving it. We're still using this same method for today. It's substitution. And you can see, once again, we have two equations here. No graphs or anything. We have to solve it algebraically. But I want you to take a look at this first. I want you to ask yourself two questions. One, which one should we tinker with? Which one is going to be easier to manipulate and get a variable by itself? And secondly, which variable should we solve for, x or y? So I'll give you a second to think about that. Now, what I would do, technically there's no right or wrong answer here. You could solve either of them and it'll work. I recommend, let's look at this one here because it's much simpler. And I would solve this equation, not for y this time, but x, because x has a coefficient of 1. So the x is already pretty much by itself here. I'll get rid of this. So all I have to do to get x by itself is subtract 4y from both sides. So you see, don't adhere to slope-intercept for this. All we have to do, the name of the game, is to get a variable by itself. So now I'm going to have x equals negative 9 minus 4y. So we have successfully defined x as this expression. So now let's go substitute it, right? So instead of writing, we're going to plug it into this next equation, the top one. So 2 times negative 9 minus 4y minus 3y equals 4. And then we're going to go ahead and keep solving this one now. So, give myself some more room here. We're going to get negative 18 minus 8y minus 3y equals 4. That's after we distribute the negative 2. Now we combine some like terms. Negative 18 minus 11y equals 4. Now I'm going to add that 18 to both sides. We're going to get negative 11y equals 22, and that's going to give us y equals negative 2. Okay, so now the only difference here is that instead of solving for x, we've solved for y. So we have half of our answer, and now we just take this y value and we'll plug it into this first equation. Again, this one here is simpler. It's easier to work with. Technically, doesn't matter. You can plug it in either one. Okay, so I'm going to do x plus 4 times negative 2, it's our y value, equals negative 9. Well, that's going to give me x plus negative 8 equals negative 9. Add 8 to both sides. I'm going to get x equals negative 1. So our solution this time, the answer to this solution of equations is negative 1, negative 2. So we'll look at a few more examples together today, but this is essentially all we're doing. We're isolating one of the variables and defining it in terms of the other. Then we're taking that expression and we substitute it into the other equation, and then finally solve for both variables. All right, more practice with that later. This is good for now. See ya.